Good morning students. Today we will discuss about black body radiation. Before going to black body radiation, we should know about what is a black body and what is the construction of black body. Later we can move for black body radiation. So what is a black body? We know that black body is a perfect absorber and perfect radiator. Means it can absorb all the radiations and it can emit all the radiation also. So when it absorbs radiations and when it emits radiations, we'll see now. Okay. Now, what are the properties? So the properties of the black body. What are the properties of the black body? We'll see now. Okay. Now, see here. These are the properties of black body. Now, what is the first property? The black body is a good absorber and radiator. Means it can absorb all the radiations and it can emit all the radiations. Next, when it absorbs, so it absorbs radiations of all wavelengths incident on it. Means it can absorb entire radiations. Whatever may be the radiation, it may be ultraviolet rays, infrared rays, microwave rays, whatever may be the radiation, it absorbs all the radiations. Next, it can emit all the radiations. It can emit all wavelength radiations, or otherwise it can emit all frequency radiations. But when it emits radiations, when it is heated. So when it is at low temperature, it can absorb entire radiations. When it is at high temperatures, it can emit radiations of all frequencies. Next, when black body is at high temperature, means when the temperature of the black body is more than surroundings, then it emits radiation more than absorbed. Means it can emit radiations more than whatever it has absorbed. Means, for example, see here, when do we call it as fever? So see here when we get fever, how can we know that we got fever? See here, when the temperature is more than surroundings, then we call it as fever. So when we get fever, what happens? Our body emits radiations, hot radiations more than absorbed. Like that only, black body also, what it will do? It will radiate more than absorbed. So these are the properties of black body. So what is black body? It is a perfect absorber and radiator. Next, it can absorb entire radiations instant on it and it can emit entire radiations but when it is heated. Okay. Next, black body can emit more than absorbed when the temperature of black body is more than its surroundings. Next, we'll see about construction. How to construct a black body. So, in order to construct a black body, let us consider a spherical cavity. So, see here, in order to construct a black body, we'll consider a spherical cavity. This is the spherical cavity. It is having small opening O. So, in order to construct black body, what we'll do is, we'll take a spherical cavity with small opening O. Next, in front of the opening, means opposite to the opening, we made a small projection. Means like this we'll make a projection. Means with the help of thermocol or otherwise granite stone, we'll keep like this. Okay. Next, here this spherical cavity is coated with lamp black. It is coated with lamp black. So what is meant by lamp black? Here lamp black means, so see here, when you lit the candle, on the wall you find black color ash like one. That we call it as lamp black. So this whole spherical cavity is coated with lamp black. So when radiation enters into this black body, what happens is it suffers multiple reflections. So it will be suffering multiple reflections inside the black body and it gets absorbed. So this happens at low temperature. This absorption of radiation takes place at low temperatures. Next, so here this spherical cavity is absorbing radiation at low temperatures. When it is heated, means when it is high temperatures. So what happens? This emits entire radiations absorbed. So these entire absorbed radiations are coming out. Okay, so from the spherical cavity, when it is heated, it is emitting radiations. So here this spherical cavity is acting like good absorber and good emitter. So it is called as a black body. Okay, so how we have constructed? So we have constructed a sphere with small opening O, and exactly opposite to it we made a small projection. Next, inner surface of the sphere is coated with lampblack. Next, when the radiation enters into the cavity from hole O, it suffers multiple reflections and it get absorbed at low temperatures, which is shown in figure A. This is figure A. Next, when this cavity is heated to high temperatures, heat radiations comes out through the cavity as shown in figure B. Okay, this is how to construct black body. Okay, next we'll move for black body radiation. What is meant by black body radiation? So see here, black body radiation means the radiation emitted by a perfect black body is called as black body radiation. So the radiation emitted by a perfect black body, when it emits radiation, when it is heated, when heated, is called as black body radiation. Now we'll see about theory of black body radiation. What is the theory behind black body radiation? Now if I go for theory of black body radiation, so see here the energy spectrum of black body can be studied. The energy spectrum of black bodies can be studied. So see here, energy spectrum means the distribution of radiant energy, means how much energy is coming out, how much energy it is radiating, black body is radiating as a function of wavelength at different temperatures. So here energy, how radiant energy is distributed with respect to wavelength at different temperatures, which can be shown in the figure. Now see here, this is the energy spectrum of black body. So if you see the curve, so this is the power radiated at each wavelength, means the power energy emitted by the black body at each wavelength at different temperatures. So see here, if we draw this graph, x-axis we have taken it as wavelength. Next y-axis we have taken it as power radiated. Now these are the different lights. These are the different radiations. Now this line, this represents ultraviolet radiations, UV radiations. Next this represents visible radiations. This scale represents infrared radiations. This is ultraviolet, visible, infrared radiations because it can emit all wavelength radiations. Okay. Now, if you see the graph, so see here the energy like this. It is increasing, decreasing, increasing, decreasing, increasing. Like this at different temperatures. It is at 1250 Kelvin, 1500 Kelvin, 1750 Kelvin, 2000 Kelvin. Okay. Now we'll draw some conclusions from this graph. So we want to draw some conclusions from the graph. Okay. First one is spectral energy density is a function of temperature. Here you can see this graph is a function of temperature. It depends on temperature. This is the first one. Next, if you see next point, at a given temperature, the energy is not uniformly distributed in the energy spectrum. Okay. Now see here. Now see here. Here. Now at a given temperature, see here, if I take this temperature 1250 Kelvin, so at this temperature what happens, energy is not uniformly distributed, it is not uniform. What happens, it is increasing and getting maximum value, later decreasing, it is not uniform. So this is the second point. So at a given temperature the energy is not continuously distributed. Next, at a given temperature, initially the radiant energy density increases with increase in wavelength. Later it decreases. Okay. Now if you see, at a given temperature, means at single temperature what happens? Initially energy increases and it acquires maximum value at lambda m. Maximum value at lambda m. And later what happens? It decreases. So what is the first point? Energy is not uniformly distributed. Next point is, as wavelength increases, energy initially increases, it gets maximum value at lambda m, later it gets decreases. Okay. Next, if we see for next point, see here, with increase in temperature, lambda m decreases. So see here, if I increase temperature, here see here, if I increase 1250, 1500, 1750, 2000, what happens? This peak wavelength is shifting towards shorter wavelength side. So it is at 3. But when it is going like this, it is shifting towards shorter wavelength side. Means as the temperature increasing, lambda m is decreasing. As temperature is increasing, lambda m is decreasing. Okay. So that is next conclusion. Next, if we go for next slide. Now see here, next point. As increase in temperature causes as increase in energy emission for all wavelengths. So as the temperature increases, so see here, you can see, as the temperature increases, what happens? This energy emitted, radiation emitted by the black body increases. So these are the conclusions drawn from theory of black body radiation from this graph. Okay, first one is energy is not uniformly distributed. Next, as the wavelength increases, energy also increases and it gets maximum value at lambda m, then it decreases. Next, at a given temperature, see here, as the temperature increases, this peak wavelength lambda m shifts towards shorter wavelength side. Next, as temperature increases, energy radiated also increases. Okay, these are the conclusions drawn from the graph. Next one is laws of black body radiation. So see here, there are 3 laws of black body radiation. First one is Stefan-Boltzmann law. So this is Stefan-Boltzmann law. So what does this law gives? It explains intensity of radiation to temperature. How intensity of radiation, how it depends on temperature. So see here, it says that the total energy emitted from a black body at a temperature is proportional to 4th power of temperature. So E is directly proportional to T power 4, which is, so it is directly proportional to T power 4. If I remove proportionality constant, E is equal to sigma T power 4. Here sigma is called as Stefan's constant. Its value is given by 5.67 into 10 power minus 8 Weber per No. Watt per meter square, Kelvin power 4. So this is about Stephen Boltzmann's law. Next, if I go for next one, this is Wien's law. So what does Wien's law explains? It explains shift in the peak of the intensity distribution. So see here it explains about, in this graph, it explains about shorter wavelength side. So it explains about the shorter wavelength, means why this wavelength is shifting towards shorter wavelength side. How this wavelength depends on temperature, that is given by Wien's law. Okay. Now Wien's law holds good for shorter wavelengths. For the shorter wavelengths it says, so the peak wavelength lambda m at which maximum emission occurs for any given temperature is inversely proportional to absolute temperature. So Wien's law says that lambda m is inversely proportional to temperature. So this I can write it as lambda mt. Lambda mt is equal to constant. So what is its constant value? 2.898 into 10 power minus 3 meter into Kelvin. This is called as Wien's displacement law. This we call it as, this we can call it as Wien's displacement law. Next, Wien's also shows that maximum energy EM is directly proportional to fifth power of absolute temperature. EM is directly proportional to T power 5. Okay. Stephen Boltzmann's law says that energy radiated is directly proportional to fourth power of temperature. But it says that energy is proportional to fifth power of temperature. Next, Wien has deduced radiation law for energy also. Energy distribution also. It is given as E is equal to C1 lambda power minus 5 exponential minus C2 by lambda T. So this is called as Wien's law of distribution of energy. This is called as Wien's law of distribution of energy. Okay. So this is about Wien's law. Next, we move for Rayleigh-Jean's law. So according to Rayleigh-Jean's law, so see Rayleigh-Jean's law holds good for longer wavelengths. Means in this graph, it explains beyond lambda m. Means below lambda m is explained by Wien's law. Above lambda m, see this peak wavelength lambda m. Below wavelength is explained by Wien's law. Above wavelength is explained by Rayleigh-Jean's law. So according to Rayleigh-Jean's law, the energy distribution in thermal spectrum is given by E lambda is equal to 8 pi kT by lambda power 4. Here K is called as Boltzmann constant. Its value is given as 1.38 into 10 power minus 23 joule per Kelvin. So these are the laws of black body radiation. So Wien's law holds good for shorter wavelengths and Rayleigh-Jean's law holds good for longer wavelengths. Okay. So this is about black body radiation. First we have discussed about what is black body. First we have discussed about, here we have discussed about what is black body, how to construct a black body, how to construct a black body. Next, what is meant by black body radiation. Next, what is the energy distribution in black body radiation. Next, about black body loss. Okay. So thank you.